Hello, grade 11 chemistry students. This um, short little video will serve as an introduction to our next unit, which is all on the topic of gases, specifically called gas laws. So the focus here of this video will be on two things. We're going to spend just a very short amount of time talking about Earth's atmosphere and the gases that make it up. Then we're going to get into the topic of pressure. I have a little simulation that I'd like to talk you guys through when it comes to pressure. So let's begin. As you know, there are gases that make up the Earth's atmosphere. Today, the composition, the amount of those gases is 78% nitrogen, 21% oxygen, 0.9% argon, about 0.04% carbon dioxide, and then a number of other gases make up the remaining percentage. This has not always been the case, and Earth's atmosphere is not stable. It has changed a lot over the course of geologic time, over the course of Earth's history, and it continues to change. So, in the Google Classroom and in class, we are going to watch some videos that are going to highlight some differences in the Earth's atmosphere at various points in the history of the Earth and some of the implications that had for life on Earth. Okay, so the next thing that we're going to talk about is pressure. So this relates to the atmosphere because the Earth's atmosphere is constantly pushing down on us in and all around us, and that there's a tremendous weight, but you don't feel it. It doesn't compress you because you also have that same air inside of your body that is pushing out. So it's in balance. Uh, but that's the idea of air pressure, is the air that's pushing down on us from above. So you can visualize air pressure as this like column of air that is pushing down on you, and the definition, the official definition of atmospheric pressure is the pressure exerted by the air in the atmosphere on 1 square meter of area at sea level. And it is measured in units called atmosphere. And there are a number of other units, but the standard unit is the ATM, and it is derived from the standard atmospheric pressure at sea level. So that is 1 atmosphere is defined as the equivalent to the pressure exerted by 34 feet of water, which is a little bit obscure, but that's what it is. And we can measure in multiple atmospheres. So as we go up in the Earth's atmosphere, the pressure gets less. And as we would go down, so imagine going down into like a mine shaft, for example, where there's even more air above you, the pressure just continues to climb because air has this mass and the Earth's gravity pulls it inwards. There's this like downward kind of pressure as you go. Okay, so as we travel to higher altitudes, there is just less air. So on this little picture that is posted in these notes, these dots represent air molecules. So close to the Earth's surface, so that's at very low altitudes, the gas molecules are clustered in there. So air pressure is a lot higher near the Earth's surface. And as you move up in altitude, the air pressure decreases dramatically. Now, this scale is on like in hundreds of kilometers. So where like even planes fly, which is at about like 5 miles, so that would be like about the equivalent to here. There's still quite a bit of air pressure, but it's not that it's noticeably different. So even people who go up climbing way on like Mount Everest that climb up there, there's only about a third as much oxygen up there as there is at sea level. So climbers need to bring their own oxygen source. Okay, I'm going to switch this over to this little simulation here. And we're going to talk a little bit more about gas pressure and how it's caused. So this is a container that you guys are looking at here. And what I'm going to do is I'm going to add some particles into it. And these are heavy particles. So I'm going to add 50 of these. Now, according to the kinetic molecular theory, all gases, ideal gases, and we're going to assume that these are ideal gases, have similar properties, and the gas itself does not matter because the distance between the gas molecules is so big that the gas itself is not consequential. So what you guys should be looking for here is, I see how these molecules are bouncing off the sides of the walls. See how they're all traveling in different directions and colliding with each other, and they're moving at different speeds. These gases would all have a temperature of 27 degrees Celsius, but that's on average. So some are going to be warmer, some are going to be colder, and remember that the temperature of a gas is just a measure of the kinetic energy of the gas. So the more energy, the faster they're moving, the higher the temperature. The other thing to notice here is that the pressure measured in atmospheres is fluctuating a little bit. So the pressure is completely caused by the gases hitting the walls of the container. It's like they're banging up and trying to like escape out of the container, and they exert a pressure on the walls of that container. And since this container is a fixed size, it's not like a balloon, there's nowhere for those gas molecules to go, so the pressure is somewhat stable. It fluctuates a little bit depending on how many collisions are happening at any given time, but you'll see that it kind of stays within this certain range. Now I'm gonna take those heavy molecules out and put in some light ones. Notice how they are moving a little bit faster on average, but the pressure that they exhibit is still about the same. So this is following those postulates of the kinetic molecular theory that the individual gas particles or molecules do not matter. It is the properties of them are going to be very similar. So notice how the pressure is about 5.5 to 6. If we put in another spray of these molecules, now we have twice as many particles, and more particles just leads to more pressure. So it's pretty much doubled. If we add in another, let's double it again, now all the way up to 200, notice how the pressure has essentially doubled again. Now we can make some adjustments, and this is going to be material topics that we're going to explore further in this unit. But if we add some heat to this system, pump up the temperature, notice how the gases are moving way faster. And because they're moving faster, because they have more energy, they hit the walls with more force, and the pressure increases. And if we do the opposite, lower the pressure, the temperature down, notice how those are slowing down. They have less kinetic energy. They hit the walls with less force, and they slow right down like that. And the pressure goes all the way down. Let's see how cold we can get this. Minus 240 degrees. There is a lower limit for temperature, which we will be looking at. It's called absolute zero. It's about minus 270 degrees. 273 degrees to be specific. And at that temperature, molecular motion ceases to exist. We're going to be able to get there. 271 minus, 272 minus. And we can't actually get to absolute zero. It's 270 minus 273.15. So we're not quite there. Let's look at it in Kelvin. That's called absolute zero because using a temperature scale called the Kelvin scale, that is 0 Kelvin. So this simulation is not 100% realistic. If we could, and that's theoretically impossible, get to absolute zero Kelvin, there would be no molecular motion. But anyways, we heat it back up and the molecules start to move a little bit faster. Temperature is slowly rising, and is it slowly rising? Now it's starting to rise. The pressure is going to slowly increase as the temperature rises. There they go. Okay, so another thing to consider here is that the size of the container also affects the pressure. So if we make this container a whole bunch smaller, cram these molecules into a smaller space, that is also going to change the pressure. Now there are more collisions with the walls because there's less space for the molecules to travel, so they're just going to hit the walls more often of the container, and that's going to affect the pressure. So notice how now we have a pressure here of about 6 atmospheres. If I put the container really big, then the pressure decreases proportionally to that. All right, I'm going to switch back to the whiteboard that we were looking at here. So your last task for this cycle is going to be to get comfortable with all of the different units of pressure. So there's one standard unit, and that's ATM, but there are a number of non-standard units, just like for length or width or whatever. We have a foot, and that's 12 inches, and that's 30 centimeters or 0.3048 meters. We have these conversions that we can use to change how we measure gas pressure, what units we use to measure gas pressure. So historically, there was something called millimeters of mercury. We'll talk about this in class, but mercury liquid, which we now know a lot more about, and the health effects of using mercury. But historically, before our understanding of mercury is what it is today, mercury was used in these devices called barometers, which measure the pressure of gases or liquids or atmospheric pressure. So the atmosphere pushes down on this, and then it forces the mercury up the tube, and at atmospheric pressure, the mercury would go up the tube 760 millimeters. So that is the unit of 1 atmosphere of pressure is equivalent to 760 millimeters of mercury, or 76 centimeters. There was an Italian scientist who made some discoveries on pressure, did some work on pressure. His name was Torricelli. So he got a unit named after him, the torr. You'll notice that the torr and millimeters of mercury are the same. Another Italian scientist named Blaise Pascal did some important work on pressure. So he had a pressure unit named after him called the Pascal. 101,325 pascals is equal to 1 atmosphere. It's a big number to work with, so we often work with kilopascals. There's a unit called PSI, which is the pounds per square inch. 14.7 PSI is equal to 1 atmosphere. In meteorology, or the study of weather, we use something called the bar. 1 bar is equal to 1 atmosphere. And because we're often using lots of bars, we talk about millibars as being another unit that is used. Okay, so your job here in the practice questions that are listed is to be able to do these conversions between different units of pressure. So one of the sample questions that's done for you here uses the concept of length and inches. So using the same idea of dimensional analysis to work with units and cancel out units, so we leave units that we need, we can see that 10 inches, which is going to be converted to centimeters, we know that there are 2.54 centimeters per inch, so that cancels out the inches unit and leaves us centimeters. So moving to pressure, we're asked to express 1.2 atmospheres as kilopascals, millimeters of mercury, and PSI. So as kilopascals, we know that 1 atmosphere is 101.325 kilopascals. You guys don't need to memorize these, by the way. On a test or exam, you'd be given those. So just know how to use them. So 1.2 atmospheres, and it's 101.325 kilopascals per atmosphere. The atmosphere unit cancels out, and we get 121.6 kilopascals. PSI, 1.2 atmospheres times 14.7 PSI per atmosphere, and we get 17.6 PSI. Millimeters of mercury, 1.2 centimeters times 706 millimeters of mercury per 1 atmosphere. We get 912 millimeters of mercury. Okay, so your job in the next little while is to do some additional practice on the topic of pressure. I've posted a couple of videos that are related to the concept of atmospheric pressure, and we will discuss these further in class. So the first 3-4 questions on this worksheet are theoretical questions having to do with pressure, and we will be discussing that in person. Pressure conversions. So if you don't need to do all of these, if you kind of understand how they work, do as many as you need, and the answer key is posted. Okay, that is it for me. Thank you very much.